So, Max, I was playing with this new AI assistant yesterday and it completely failed to understand what I wanted it to do.
Let me guess. It couldn't predict what actions you were going to take next?
Exactly. It's like it had no concept of how the real world works. I mean, shouldn't AI be able to understand the consequences of actions by now?
Funny you should mention that, because that's exactly what today's paper is about. Teaching AI to understand actions and their consequences in the real world.
Welcome to another episode of Totally Unprofessional Peer Review. I'm Casey Park, your developer host who's obsessed with structure and flow.
And I'm Max Stone, your friendly neighborhood theorist who's all about metrics and methodology.
Today we're diving into a fascinating paper titled Learning Latent Action World Models in the Wild, which tackles a major challenge in AI: how to build models that can predict action consequences from real-world videos.
What makes this paper interesting is that instead of using labeled actions or controlled environments, they're trying to learn directly from diverse, messy, real-world videos.
Right, and they're doing this by learning what they call latent actions, essentially discovering the underlying structure of actions without being explicitly told what those actions are.
The researchers found that continuous latent action spaces work better than discrete ones for capturing the complexity of real-world actions. They're basically teaching AI to understand the world by watching YouTube.
Which is funny because that's how I learned to fix my dishwasher.
And change your oil, and build that bookshelf, and
Okay. But seriously, what's fascinating is that even without consistent embodiment across videos, meaning the same agent performing actions, their models still learned useful action representations.
they showed these representations can be used for planning tasks with performance comparable to models that were explicitly given action labels. It's like learning to drive by watching traffic cams instead of taking lessons.
So stick around as we unpack how these researchers are teaching AI to understand the consequences of actions in the wild. Because if my smart home is ever going to truly understand me, it's going to need this kind of technology.
And maybe then it'll finally stop turning on your kitchen lights when you ask it to play music.
Let's dive into the details of how they're building these world models and the specific challenges they face when working with in the wild videos.
So let's talk about the core concept here. What exactly is a latent action world model?
At its heart, it's an AI system that can predict the consequences of actions in the real world. But here's the twist: it learns to do this without being explicitly told what those actions are.
Right. Traditional world models require labeled actions like pick up cup or turn left, which are incredibly difficult and expensive to collect at scale.
Exactly. But these researchers are saying, what if we could learn the underlying structure of actions just by watching videos? They call these latent actions, representations, the model discovers on its own.
And what makes this paper particularly interesting is that they're doing this with in the wild videos, real-world footage that's messy, diverse, and unpredictable, not just controlled lab environments or video games.
This graph really illustrates the challenge. Previous work focused on navigation tasks, manipulation tasks, or controlled environments where actions are limited and well-defined. But in the wild videos contain a much wider range of possible actions, making the problem significantly harder.
And notice how the presence of different action types varies across these domains. In the wild videos have this long tail of diverse actions that are much harder to capture.
So how exactly does a latent action model work? Let me break it down. Instead of being told this is a walking action, the model has to figure out the underlying pattern that represents walking just by seeing the before and after states in a video.
Right. It's using what's called an inverse dynamics model, or IDM. Basically, it looks at frame t and frame t plus 1 and tries to infer what action must have happened to cause that change.
Looking at this diagram, we can see how it works. The model takes video frames as input, and that function g-phi there is the inverse dynamics model that infers the latent action z by looking at consecutive states.
And then, that latent action is fed into a forward prediction model, f theta, which tries to predict the next state. The whole system learns by minimizing the difference between its predictions and what actually happens next in the videos.
One key insight from this paper is that the representation of these latent actions matters a lot. The researchers found that continuous latent actions work better than discrete ones for capturing the complexity of real-world actions.
Let's look at some of their results. This image shows how different types of latent action representations perform when predicting a person walking into a scene.
The top row is ground truth, what actually happened. Then we see predictions using sparse latent actions, noisy latent actions, and discrete latent actions at the bottom. Notice how the discrete representation completely fails to capture the person entering the scene,
While the sparse and noisy continuous representations do a much better job. The paper mentions that continuous but constrained latent actions are able to capture the complexity of actions from in-the-wild videos in a way that vector quantization approaches can't.
And here's a chart showing the prediction error for different approaches. Lower is better here. The sparse and noisy approaches give a range of performance that's better than the discrete approach.
What's interesting is that the researchers found that achieving the absolute lowest prediction error isn't always desirable. There's a balance between complexity and making the latent actions identifiable and useful for downstream tasks.
Another fascinating capability they demonstrated is action transfer between videos. Essentially, they can take an action from one video and apply it to another scene.
Right, in this diagram, they're showing how they can infer latent action from video A, apply it to video B, and then transfer it back. It's like saying, take the walking motion from this beach scene and apply it to this indoor scene.
And we can see the results here. They take the action of a person walking from the source video at the top, and even though the middle video is completely different, it looks like a landscape with a purple ball, they can transfer that walking action to another indoor scene at the bottom.
This is pretty remarkable because it suggests the model has learned something fundamental about the structure of actions that transcends specific videos. It's learning a kind of universal action language.
One limitation they found is that without a common embodiment across videos, meaning the same agent performing actions, the latent actions tend to become localized in space relative to the camera.
Let's take a look at what that means in practice. Here, they're showing how the model can animate different people in a scene.
Right, so they can specifically target whether they want to animate the person on the right or left side of the frame. This suggests the latent actions are indeed becoming spatially localized.
Despite these challenges, they were able to train a controller that maps known actions to latent ones, allowing them to use these latent actions as a universal interface for planning tasks.
And impressively, their model performed similarly to action-conditioned baselines on these planning tasks, even though it had to learn the action space from scratch.
So to sum up, they've shown it's possible to learn useful world models from in-the-wild videos without explicit action labels, which is a significant step toward more generalizable AI that can understand and predict the consequences of actions in the real world.
And that's huge because if we want AI that can function in the messy real world, it needs to understand the cause and effect relationships between actions and outcomes in all their complexity, not just in simplified environments.
Exactly! It's the difference between an AI that can play chess and one that can help you navigate a crowded grocery store.
Or one that understands that when I say turn on the lights, I don't mean play my workout playlist at maximum volume.
Speaking from experience there, Casey?
Let's just say my neighbors now know my workout playlist better than I'd like. But that's exactly why this research matters, building AI that truly understands the consequences of actions in the real world.
Now let's dig deeper into the unique challenges of learning from in-the-wild videos. This is where things get really interesting.
Right. So far, we've talked about the general concept, but what makes in the wild videos particularly challenging compared to controlled environments?
Well, there are two major challenges. First, in-the-wild videos contain a lot of environmental noise, things like leaves rustling in the wind or lighting changes that aren't actually meaningful actions.
And the model has to somehow figure out which changes are important actions and which are just background noise. That's tough.
Exactly. The second major challenge is the lack of a common embodiment across videos. In robotics datasets, you have the same robot performing actions. But in YouTube videos, you might have humans, animals, vehicles, all kinds of different agents performing actions.
Let's take another look at that distribution graph from earlier. It really illustrates how in the wild videos have this long tail of diverse actions that are much harder to capture.
And the paper mentions that the very concept of what constitutes an action becomes fuzzy in these diverse videos. It's not as clear-cut as turn left or pick up objects like in controlled environments.
So, how did the researchers address these challenges?
One key insight was that they needed to carefully constrain the information content of the latent actions. Let's look again at their model architecture.
Right? And on the right side of this diagram, we can see different approaches they tried for constraining the latent action space: noisy, sparse, and quantized.
The paper points out that if you don't constrain the latent actions at all, there's a risk that instead of learning meaningful actions, the model will just encode the entire next frame in the latent space, essentially cheating at the prediction task.
And that wouldn't be useful for understanding actions or planning. It would just be memorizing sequences.
Exactly, so they experimented with different constraints. The noisy approach is similar to a VAE, adding stochastic noise to prevent the latent space from encoding too much information. The sparse approach encourages most dimensions to be zero, and the discrete approach uses vector quantization.
And what did they find worked best for in the wild videos?
Interestingly, they found that continuous but constrained latent actions, either the sparse or noisy approach, worked significantly better than discrete ones for capturing complex real-world actions.
We can see that clearly in these prediction examples. The discrete approach at the bottom completely fails to capture the person walking into the scene, while the sparse and noisy approaches do a much better job.
This is a key finding of the paper. The continuous latent actions are better suited for the complexity of in-the-wild videos than the discrete approaches that had been common in previous work.
Let's look at the quantitative results. This chart shows the prediction error for different approaches, and we can see that sparse and noisy approaches consistently outperform the discrete approach.
But interestingly, they note that achieving the absolute lowest prediction error isn't always the goal. There's a balance between minimizing error and learning meaningful, useful action representations.
Now let's talk about the second major challenge, the lack of common embodiment across videos. How did they address that?
This was a fascinating finding. They discovered that without a common embodiment, the latent actions naturally become spatially localized relative to the camera.
That makes sense when you think about it. Without a consistent agent performing actions across videos, the model learns to associate actions with regions of the frame rather than with specific agents.
Right. As this takeaway slide summarizes, the absence of clear embodiment in natural videos leads to latent actions capturing more spatially localized camera-relative transformations.
But despite this limitation, they were still able to use these latent actions effectively for planning tasks, right?
Yes, and that's what makes this work so promising. They trained a controller that maps known actions to latent ones, essentially creating a universal interface for planning tasks.
Looking at these results, we can see that their approach, labeled IDM for Inverse Dynamics Model, performs comparably to models that were explicitly given action labels. That's impressive considering they had to learn the action space from scratch.
And they demonstrated this on both robotic manipulation tasks, DROI'd on the left, and scene reconstruction tasks, Reckon on the right.
So, to summarize this section, the researchers faced two major challenges when learning from in-the-wild videos: environmental noise and lack of common embodiment.
And they addressed these challenges by carefully constraining the latent action space, finding that continuous but constrained representations work better than discrete ones, and by leveraging the naturally emerging spatial localization of actions.
The result is a world model that can learn meaningful action representations from diverse, messy, real-world videos without requiring explicit action labels, which is a significant step toward more generalizable AI systems.
And critically, these learned latent actions can be used effectively for planning tasks, performing similarly to models that were given explicit action labels.
It's a great example of how embracing the messiness of real-world data, rather than trying to simplify it away, can lead to more robust and generalizable AI systems.
Absolutely. Now let's move on to discuss the specific architectural choices they made and how those affected the performance of their world models.
Let's dive deeper into the architectural choices the researchers made for their latent action world models. This is where we really see what makes their approach unique.
Right. The key innovation here is how they designed the latent action space. Let's take another look at their model architecture to understand the different approaches they tried.
So on the right side of this diagram, we can see they experimented with three different ways to constrain the latent action space: noisy, sparse, and quantized or discrete.
Exactly. The noisy approach is similar to a variational autoencoder, adding stochastic noise to prevent the latent space from encoding too much information. The sparse approach encourages most dimensions to be zero, and the discrete approach uses vector quantization.
But why constrain the latent action space at all? Why not just let the model learn whatever representation works best?
That's a great question. The paper points out that if you don't constrain the latent actions, there's a risk that instead of learning meaningful actions, the model will just encode the entire next frame in the latent space, essentially cheating at the prediction task.
Right, it would just memorize the sequence rather than learning a useful abstraction of actions. So they needed to find the right balance. Enough information to capture meaningful actions, but not so much that it just memorizes the entire sequence.
And what they found was really interesting. For in the wild videos, continuous but constrained latent actions, either the sparse or noisy approach, worked significantly better than discrete ones for capturing complex real-world actions.
We can see that clearly in these prediction examples. The discrete approach at the bottom completely fails to capture the person walking into the scene, while the sparse and noisy approaches do a much better job.
This is actually a departure from previous work in this area, which often used discrete latent action spaces. The researchers found that for the complexity of in-the-wild videos, continuous representations are just better suited.
Let's look at the quantitative results. This chart shows the prediction error for different approaches, and we can see that sparse and noisy approaches consistently outperform the discrete approach.
But interestingly, they note that achieving the absolute lowest prediction error isn't always the goal. There's a balance between minimizing error and learning meaningful, useful action representations.
They actually use something called variance, covariance, mean regularization, inspired by VicReg, to ensure an adequate spread of information in the latent space. This helps prevent the model from learning shortcuts or trivial solutions.
And they also found that the capacity of the latent action space, how much information it can encode, has a significant impact on performance. Too little capacity, and it can't capture complex actions. Too much, and it starts encoding irrelevant details or noise.
One of the most impressive capabilities they demonstrated was action transfer between videos. They could take an action from one video and apply it to another scene, even when the scenes were completely different.
Right, this diagram shows their approach for testing action transfer. They infer a latent action from video A, apply it to video B, then infer a new latent action from the prediction, and apply it back to video A.
By measuring the increase in prediction error, they can see how well the latent actions transfer between videos. It's a clever way to test if the model is learning meaningful action representations rather than just memorizing specific video sequences.
And here we can see some results of this transfer capability. The top row shows the ground truth, what actually happened. The middle rows show predictions with different capacity models.
It's impressive that even with the low capacity model, they can still capture the essence of a person appearing in the scene, even though the details are blurry. This suggests the model is learning something fundamental about the action of a person entering the frames that transcends specific videos.
Here's a table showing the quantitative results of their transfer experiments. The numbers in parentheses show how much the error increases when transferring actions between videos.
And we can see that for all approaches, sparse, noisy, and discrete, the error increases by similar amounts when transferring actions. This suggests all these approaches are learning transferable action representations, though the continuous approaches still perform better overall.
Now, let's talk about how they use these latent actions for planning tasks. This was one of the most impressive aspects of the paper.
Right. They trained a controller that maps known actions to latent ones, essentially creating a universal interface for planning tasks. This diagram shows the architecture of that controller.
And here are the results of using that controller for planning tasks. They tested on both robotic manipulation tasks, DROI'd on the left, and scene reconstruction tasks, RECON, on the right.
What's impressive is that their approach, labeled IDM for Inverse Dynamics Model, performs comparably to models that were explicitly given action labels. That's remarkable considering they had to learn the action space from scratch just by watching videos.
And we can see that visually here. The top row shows ground truth, the middle row shows their IDM approach, and the bottom row shows the controller approach. Both approaches do a good job of matching the ground truth sequences.
They also did some interesting scaling experiments. This figure shows how performance changes when scaling model size, training time, and training data quantity.
For all three scaling axes, they were able to obtain improved performance on natural videos, top row. And when measuring performance on planning tasks, bottom row, they saw similar trends, with the clearest improvements coming from training longer.
What's interesting is that they found a lack of correlation between prediction error on in the wild videos and the quality of rollouts when using the controller. For both sparse and noisy latent actions, they found that using the most or least constrained setting was suboptimal.
Right, they found that a more balanced regularization leads to the best predictions. This makes intuitive sense. Over-constrained latent actions don't contain enough information, while under-constrained ones contain too much information about the future.
So to summarize the architectural choices, they found that continuous but constrained latent actions work best for in the wild videos, with either sparse or noisy constraints performing better than discrete approaches.
And they showed that these learned latent actions can be used as a universal interface for planning tasks, performing similarly to models that were given explicit action labels. This is a significant step toward more generalizable AI that can understand and predict the consequences of actions in the real world.
What's particularly impressive is that they achieved this using only in the wild videos, without requiring expensive labeled datasets or controlled environments. It really opens up the possibility of scaling these models to learn from the vast amount of video data available on the internet.
Exactly. By showing that continuous latent action spaces can capture the complexity of real-world actions and be used effectively for planning, they've made a significant contribution to building AI systems that can understand and operate in the messy, complex real world.
And that brings us to the end of our deep dive into this fascinating paper. We've covered how they built world models that can predict action consequences from in the wild videos, the challenges they faced, and the architectural choices that made their approach successful.
It's a significant step toward AI systems that can understand the physical world in the way humans do, by observing, inferring cause and effect relationships, and using that understanding to plan and act effectively.
And maybe someday soon my smart home will finally understand that when I say turn on the lights, I don't mean play my workout playlist at maximum volume.
We can only hope, Casey. We can only hope. So to wrap things up, this research represents a significant leap toward AI systems that can truly understand the physical world through observation rather than explicit programming.
Absolutely. By learning from messy, real-world videos instead of controlled environments, these models are getting closer to understanding actions and consequences the way humans naturally do.
And the potential applications are enormous, from more intuitive smart homes to robots that can adapt to new environments without extensive reprogramming.
Thanks for joining us for another episode of Totally Unprofessional Peer Review. If you enjoyed this deep dive, be sure to subscribe for more cutting-edge AI research breakdowns.
And remember, you can find links to the paper and additional resources on our website.
Until next time, I'm Casey Park.
And I'm Max Stone, reminding you that while AI is learning to predict the consequences of actions, my predictive model says there's a 99% chance Casey will still be arguing with his smart home next week.
Hey, at least now I know my smart home isn't failing to understand me, it's just conducting latent action research on my patients.